I still get the kind of interesting reaction from people when I say I work for Bell Laboratories, and then I have to say, it belongs to Alcatel-Lucent, a French company, and people cannot get over the fact that so many things happen over the last 20, 30 years in our industry, and it's just the amazing transformations that is happening, and it will continue to happen. I believe it's going to be more, accelerated more, not less. So today I will talk about maybe 3 challenges as I see it in our industry. They are not by any means a complete, but they are substantive area of challenges. And then I'm going to talk about the innovation, which is more general subject. At least my thought about that. So the first one is really the frontier. If you think about our industry, first network, electronic networks is all about telephones, right? Telephone was the way to get to other people that you want to communicate to, and everything that was designed to support the quality and amount of traffic that's going to carry by your telephone phone calls. So today we have a little over 6 billion people, and if you were to have everybody talking simultaneously, so that's like 3 billion phone calls, amount of traffic that's going to be required is, today you carry about 8 kilobits per second type of a transmission for your cell phone or voice over IP phones. That's 24 terabits. Well, we can actually transmit more than 25 terabits per second over a single fiber. So so you have to think. I say this because you have to put a different mindset as I talk about the network of today, which is much more data centric, and the network of the future, which is more of a sensor centric. And also the focus was really on differing the distance, getting a connection to everywhere. Well, then came computers and liberation of computers, and the amount of traffic the computer generates is a factor of maybe 500 times more, and it is expected to grow, more as time goes on. So, type of network that is required, besides that you are talking to computers and computer to computers and so on, has to be architected differently. You just cannot have a type of circuit-based network that we had for voice and then expect it to just, put overlay on it. So what transformation that is happening in our industry is basically going from the circuit-based network, which is primarily designed to carry voice, to a packet-based network, which is designed to carry data and then put the voice in overlay. And in terms of focus, in terms of applications, is once we defeat the distance, AT&T and others give you a flat rate, a pricing for all your long-distance phone calls and so on. It's really focused on managing your proximity. We are much more interested, when I come to Santa Barbara, where it's a place to stay, where the kind of restaurants that I like to go to. Or if you are driving, what the traffic conditions are. It's really about using the information in the network to control the proximity. So this is what I expect to face. We are already facing this today, but this is what I expect to face in a much more significant way. Is that our network, basically designed for computer networks, is going to change to more sensor-based networks. Jim talked about all the sensors that he needs for run his utility network. But think about when you go to a city, all the video cameras in the intersections is feeding the some storage 24/7. All these video signals everywhere, right? And matter of fact, a current network is not capable of actually transmitting that much video traffic. So actually taking out capture data and sending. But the idea is that there will be a liberation of sensors, and when those things happen, the amount of traffic that will be generated from the load on the network will be another factor of 500 to 1,000 times more. So we have to think about how the network will evolve, besides just normal increase in traffic, because everybody today talk about more video on the network and so on. That gives you, a big jump, but not the kind of increase that I'm talking about. Also, the focus of the use of network will be much more closer. Once we conquer controlling our proximity, we would be interested in having a network to assist us in a very personal way, whether it is about having a smart homes with the sensors to tell you what to do and so on, but also about your body. You can easily imagine having a nano-based sensors implanted that actually give you and react with you in a real time. That is very helpful. So I want to talk a little bit about some sensor technology. And what I'm showing here, I guess point that I want to talk about sensor technology is that even though we can transmit 25 terabits per second on over single fiber, I cannot communicate with my laptop at probably no more than a few bytes per second because I have to type it in. And I think once we conquer the last mile, which is what we are trying to do, we need to conquer the last inch. And we need to have a very smart sensor to be able to do that. We need to be able to communicate with machine as naturally as you and I can communicate on human. So some of the research that we are doing, some of the technology we're working on are nano-based sensors. What you see on the video here is an electronic cornea. It's a drop of water on the top of a nano structure like this. It's like a bed of nails. Because it has a large amount of surface area, that surface tension forces a water to basically suspend in the air. Gravity is very negligent. So what you do is you apply voltage to the surface, and then you can actually wet the drop of water, and you can actually control the shape of this droplet of water any way that you like. So you can have a zoom in, zoom out, and so on. And so you can put this, you can imagine one day, in a zero gravity type of packaging and be able to have a cameras everywhere, not using the very expensive, the lens that we have on our cell phone, everything else, but have much more effective type of lens. Of course, what you're seeing here is a picture of microphones. Microphones we use today are basically the same technology that was developed by Jim West many years ago. Over 90% of the microphones being used today is still based on some of the work that he has done. And I think we really haven't invested in the industry to make it better. So, of course, in the future, the hope is that we don't have to carry a microphone like this. Microphone can be embedded everywhere, on the wallpaper or your clothes, so it's not a separate device. I talk about the importance of having sensors that really affect the quality of your life. There's nothing more important than worrying about your own health. So here's a real fun research project that one of my researchers has done, is that without any kind of hardware modification, just using software, what he did was he basically take the signal of the cell phone off the network, because your cell phone sends the signal about I'm alive, and so on, and the signal bounces off your chest. Because you are breathing, Doppler effects can cause observe the signal to be like this, and then you can apply filter, and if you compare to the base reference of heartbeat, you can actually monitor your heartbeats real time, and this can be done today. And of course, there are all kinds of neat sensor technologies that people are working on. But this is when I show this thing to people get pretty excited about this, because it's not intrusive at all. Now we are also working with a Pittsburgh Medical Center to integrate all these different type of sensors, and then make some sense out of it. Because in the hospital, you have all these sensors to track people, track equipment, and it's quite challenging task. And you need a system that not only monitor what's going on, but process it, make some sense out of it, and be useful in assist you in some way. So it's a fairly big project. And again, the research in this area is quite challenging. So I'm going to talk about the next challenge, as I see it. It's about the information onslaught. I think all of you agree that the time is the most precious commodity that we have. We only have one life to live. And as you get older, you realize time is flying faster, faster, and faster. And then one day, you die. So according to the study conducted by School of Information Management at UC Berkeley, in the 1999, the world has produced and stored approximately 3 exabytes worth of data. Okay? The follow-on study 3 years later showed that the world has estimated to be about 6 exabytes worth of data. So if you can extrapolate that to today, it may be 12 to 15 exabytes of data. It's been created this year alone and being stored. And either continue, either never disappear, either be stored forever, and so on. On the other hand, people like you and me, we were cute baby once, and then we eventually grow, older and wiser. But we basically hit the plateau in terms of how much you can actually learn and retain. That amount is estimated to be several hundred megabytes. That's it. So the gap between the amount of knowledge being created and stored and amount of knowledge that human can carry in our brain is growing more and more. And it's called like a time knowledge gap. So this creates incredible challenge for our industry, but also incredible opportunity for all of us. So consider Google today. Everybody excited about Google. Well, they have a very clever search engine, and they are estimated to use several petabytes worth of RAM in assistance of their search engine. But that's minuscule. That's very basically scratching the surface with respect to how much of information there is available and being stored. So there's so much opportunity in my mind in our industry to really do something about this particular phenomenon. So I have a very low voice, so I have a tendency to put people to sleep, especially when I give a lecture after lunch. So I normally ask a question to see if you are listening to me. I want to conduct an experiment, and this is a very simple experiment. And I will tell you that it's not as easy as it may sound. The challenge is to count the number of the balls, basketballs, people wearing the white jersey pass to each other. Okay? That's it. Just count the number of times the players, the students pass the basketball to each other. It's not 1, it's not 2, it's not 3, it's a lot more than that. And I will dare to say very few people are going to get it right. I've done it a few times. Okay, so you ready? Okay? And I'm going to ask you what you think it is. Here you go. So how many do you think, how many people think there were 16 passes? Raise your hand. How many counted 17? How many counted 18? Okay, so right answer is 18. And of course you can have the video to count very slowly. But how many of you have seen other things? Raise your hand. Okay, so about maybe 30%, that's about right. Okay, so watch it again. Okay, this time don't count the passes, but just watch. Excuse me. Okay, how do I do this? So honestly, how many of you missed the gorilla the first time? Raise your hand. See, quite a few. But there's a good reason for it, because I set you up. I set you up to concentrate on passing balls. So point that I want to make is that we have a built-in mechanism to deal with information overload. There's a lot of information that is available with your eyes, but you tend to focus on the things that matters to you, right? We have a mechanism to deal with it. And like I said, amount of information you get simply by your visual image is over a petabyte per year. But amount of information that is being processed and stored in your memory is much lower than that, right? So you have a personal semantic map that help you with a filter, but also help you process it, put it in the memory. So when I say friends, I don't know, you may think of food, you may think of wine, maybe you may think of totally friends. I think of Bell Labs. So everybody has different reference for thinking about different information. So having this kind of research is really critical because, like I said, that challenge that I share with you, the time-knowledge dilemma, it's not going to go away. It's going to get worse and worse. And so what we can learn from how we deal with it in real time can also be useful in some sense. So with this all the sensors, what I'm showing here is the sensors, we give you the information in terms of context. Because network of the future has to provide information, not just simple connectivity or need applications, but very personalized. Either for you as a person or for the entity as enterprise and so on and so forth. And it has to have a right kind of context, and sensor will provide any input. And then you have to have a resources, the servers that basically tell you what resources are available in terms of being able to process it, contact you, and so on. But you also need the policies for really many different groups. It could be a policy for each person. You have personal preference, and you need to do certain things way. You can either tell them what you like, or you can have a network or machine can learn from you, and then deal with it, and so on. But that's totally different than having an entity, let's say enterprise, having its own policy. For instance, using this computer, which is my company's computer, I don't have my way to do things. There are certain things that I cannot get in. It's blocked. Certain software patch has to be uploaded. So there are policies designed for personnel. There are policies designed for the enclave, for your enterprise, for instance. There are policies that maybe dictate your community of interest or advertisers who are interested in hooking up right kind of sellers and buyers. And these kind of policies all has to flow together in order to create what I call the context-aware network. And these are huge challenges. And we believe that there are many clever things that we can do to make life easier. But if you just think about the amount of information that needs to be processed, sometimes you just need a better computer, better machine, right? I mean, today's computer simply won't cut it. If you think about all the information that's going to be created, how are you going to process all this? Well, so quantum computer is something that we take a very serious interest because promises that it can do certain things much better than silicon-based logic computers. Right? Such thing as doing a factorial calculations, or solving the traveling salesman's problem, or searching large databases. How much faster? A theory is at least 10 million times faster. So there are many ways to develop quantum computers. The approach we are taking is develop the ion trap. Matter of fact, when I first joined the lab, within a couple of months, one of my researchers came into my office, got really excited at the fact that he actually built the first ion trap, had fairly long stability, and long being like a week or more, and built and tested at the Oak Ridge National Lab. And of course, that was my introduction to the work that we are doing here. But this kind of work, it takes 10 years to do, maybe more. But you can imagine why we believe that we need to do this. Because without doing it, then I don't know how we can actually solve some of the problems that I see that is coming down the road. By the way, I didn't intend to make it talk technical. I mean, we could talk technically, but I think that's not the session, just to try to share the insights. So I apologize. You can ask me a question if you like later. So third area, as I like to share my thoughts, is, with all this wave of innovations, something's happening to our society. And that has to do with the shortening of the generation gap. When we talked about generation gap, when I was growing up, we were talking about me and my father, or my parents, or my grandfather. Today, if you ask Tony something, they will say, they will point out that they have a generation gap with the teenagers. And they just have a different mode of operations, they have a different culture. Why is that? Well, Kevin Kelly, who was the first editor of the Wired magazine, has a theory that, based on his theory and my application of Moore's law and so on, basically when you have about 500 times increase in price performance, there's a major cultural shift. And if you apply that to today's environment, it's about every 10 years or so. So these are my words in terms of how I categorize each of this decade. But just like we think with our language, our work behavior, our organization behavior, where we conduct our business, is all influenced by the kind of tools that we have in terms of communication tools, computing tools. So we come from IBM mainframe to server client environment to personal computers and so on, and of course going from a simple telephone to mobile phone and so on and so forth. All those things get influenced. So when I started thinking about this kind of challenges, problems, this was about maybe 10 years ago. What I thought we'd be living, which I think I sort of guessed it pretty right, was what I call equalized. Is that a lot of social network, not necessarily a hierarchical structure, which is really copied from the military structure to fight the war, but very, very different type of requirements. And then I think these are fairly obvious that you guys are familiar with. What I think about the future is what I call quantumized. As I think about all this information that is out there, one thing for sure is that we can never have a high degree of confidence about the information itself. You need to make decisions on some probability with some uncertainty about the information. Whether it's a search engine, whether it's whatever the source is, you don't have time to check everything. And I think, again, culturally, it is more acceptable with a bunch of kids growing up watching ESPN and Texas Hold'em. They're calculating the betting probability real time. I think they're fairly comfortable with that. So maybe that's the way it goes. But maybe it's not the right term. English is not my strong forte. But that's what I mean by that. So I talked about our industry in such a dynamic state of change. So if you were to ask me, what does a company like Lucent, before that, it was Western Electric, now Alcatel-Lucent, do? Well, we build a network. We build a network because Bob McAfee said the value of network increases with the square of each node, meaning that the more people are connected, it's more useful. not just linearly, but within square function. Well, that's why everybody went out, tried to build all this network, build a backbone, build an access network, try to bring everybody. AT&T's main mission was universal access, right? Get everybody connected, communication, any place, anytime, anywhere. That was this mission. Well, problem is that the distribution portions of the networking is only a small portions of it. Simply connecting to a network, connecting to people, connecting to computer is not good enough. We are taking that for granted. What you really need is something that increases the quality of our life. What are those things? Well, those things are like insight, entertainment, awareness, socialization. When you go to art library, right, or museum, you gain so much more out of it when curator walk around with you, tell you about the background of the painting, about the artist, because you get a better insight. And it's valuable to you if you're going to a museum tour. So what the network has to do is to provide this kind of a valuable things. Otherwise, they don't want to pay. Or if they want to pay, they want to pay minimum. So industry has become basically focused on distribution, which is becoming increasingly commoditized to much broader in terms of sending the right content at the right people, at the right place, at the right time, and just the right amount, right? When I talked to Bob McAfee last summer, I actually pointed out to him that his law is no longer valid. I told him that it was valid until network reached the critical mass, but actually that more you add, things get more complicated, actually has a less value. But I compromised on this. I said potential value of a network may continue to increase. So challenge for our industry is to translate the potential value into real value. So you could see why a company like Google, based on the search engine, could excel, because it adds some value. So I'm going to move on to the last subject, which is about innovation. Everybody talk about innovations, and I get asked, come and talk about innovations in many places. One place I did not expect was China. They said they want me to come and talk to Chinese Communist Party school. So I said, why would I want to do that? Because being a former military officer, I was a former nuclear submarine officer for U.S. Navy. My immediate reaction was, why? When you say Communist Party school, it just didn't sound right. And then they went through what this was. This is not a school for anybody, but it is really a school for the decision makers, ministers, and I'm sure our Chinese colleagues here probably have a better appreciation what it is. I'm like only one of the few foreigners to ever even be invited to come and give a speech, and it's a great honor, which I didn't particularly care for. But so I said, what do they want me to talk about? He said, well, they want me to talk about innovation. China has a goal of trying to achieve indigenous innovation, within a certain time period. They actually stated that in their 5-year mission, and they want me to come and talk to Chinese ministers about innovation. So, and my inclination was, why would I want to go talk to them? But they say it's going to be incredibly helpful for our business and so on. And so they twisted my arms. I said, okay, I'll do it. And then I started sweating because I said, what am I going to tell them? I mean, these are smart people. I'm sure they talk to a lot of people. So I started jogging, and I was thinking about this, and I realized people think with language, right? Because you can say English is not my native tongue, so I think with my native tongue and so on. So I wonder what Chinese people thought innovation was. It's not a Chinese word, so I'm not Chinese, by the way. I mean, I may look like one, but I'm not. I'm Korean. So I asked, I don't read or speak Chinese, so I asked my Chinese colleagues, how do you write innovation in Chinese word? And they wrote me, and of course I don't understand it because I don't read Chinese. But what I noticed was that not everybody was writing the innovation in the exactly same way, because I wanted to understand what they thought innovation was. So I was thinking about this, and I opened up a Webster's dictionary and looked them up. How does dictionary defines innovation? It defines innovation as the introduction of something new, effecting change. So it defines the innovation in 2 dimensions. One is the creation process. The other one is the impact. Right? So being a industry person, I ask the most important question in my mind. That is, why does anybody care about innovation? Why does China care about innovation? Well, China cares about innovation because they believe the innovation will lead to improved competitiveness in the world market, and they will eventually translate into better return and improve the quality of your life. Right? That's true for countries. That's true for companies as well. So if you really think about that and think about all the dynamic, accelerated pace of changes that are taking place, then that definition of Webster's dictionary, that definition is not sufficient. Okay? So what's missing? There's a timing. Timing of creation process, timing of impact. The good old days where we can take our time to do the things right and so on. It's different. It's different today. World is flatter, faster, clocks are ticking a little faster and so on. So I believe that innovation needs to think in 3 dimensions, not just in creation process and impact, but timing. So let me say what the process is. Process, on one end, I call that analytic. Analytic is a process being used when the outcome is known. So you are trying to solve a particular problem, so you are applying systematic approach to solve a particular problem. Artistic process, on the other hand, is that you don't know what problem you are solving. You're just interested in research because it fascinates you. And then, but maybe you're gonna get a eureka moment because you carry with you a set of problems that you think about, that this knowledge you gain through research maybe help solving the problem. You don't really think actively, but that's what you do. So it is more of artistic. And of course, in terms of impact, it could be incremental impact. It could be a disruptive, revolutionary impact. And third, in terms of timing, it's very obvious, either current market or future market, right? Okay. So one way to really understand this innovation cube that I created is actually, as all of you engineers probably think, understand the boundaries. Look at the boundaries and behaviors, and you understand what this is. So if you look at the low impact plane, what I call that incremental, if you look at the one corner, here, they're talking about trying to solve today's problem, known problem, and using analytic process, and the impact is incremental. That's what most of our engineers do, to develop the next releases, okay? Next generation product, develop the needs requirements, translate into specification, and then go on from there, right? That's the status quo. If you use a PhD researchers, as some of us have done in the past, to do software testing, or something that does not use true talent, it's a diversion. The guy who's not really trained to apply those, the category of people here is more engineer trained. Category here more science trained, right? That's sort of a difference. So when you use those highly valued resources in such a incremental impact type of effort, then it's what I consider diversion. Here is about the future market that has a very small market impact. Actually, you may laugh, but a lot of people actually do this, especially people who try to get a PhD. They got to find something original. So they try to find something that nobody has thought about, probably doesn't have a whole lot of relevance, because that's why I don't really work on it. But it serves the purpose of getting the original research and get published. I may be saying a little too harsh, but all of us went through a PhD process, thought about it anyway, right? Taking the easy way out. But you may publish papers, but it's sort of pointless from the industrial research perspective. That is. Well, anyway, you can go through all these things. But the more interesting plane is what I call high impact plane. This corner is today's market, and if you solve the problem, it will make a major impact, we believe, and therefore you can actually make lots of money. It is serving today's market. And there, what you need is entrepreneurs. Entrepreneurs who apply best practices in the industry, think out of the box, and just it's all about solving the problem, getting the solutions as fast as one could. You can apply in small startups, you could apply in big organizations. So my example is one of the projects we launched in our laboratories a couple of years ago. It's called the laptop EVROS project. This project has to do with solving laptop problems. Okay? There are more laptops being sold than desktops. We all know that. And there are more laptops being lost or stolen every year. Over 600,000. That was the data a couple of years ago. I'm sure there are more. And of course, laptop is valuable because you have to pay for it, but data there could be really valuable, right? So we need to solve that problem. Every CIO has that problem. Well, we decided to work on it and we actually solved the problem. We solved the problem by actually having one of those PC card, 3G card, the PCMCIA format for now anyway. You plug it in. This is my data card. That has processor, memory, and battery in it. So even though when you turn off the computer, it's always on. And it's connected to the network. And the computer only work through the encryption scheme that connected through this card. So if you pull out, it don't work. Okay? The key to the encryption is not on the card or on your computer, but in your corporate server, somewhere else. So if somebody stole your computer, we have absolute control of the, of the data and what to do with it. So, every CIO that I met, the first thing that they say is, where can I buy it? I mean, I got a call from the Federal Express on our 800 number. They said they heard us from somebody that this such product exists, we want to buy it. We are being a laboratory research organization. We had to transfer the project to the business group so they can do this. So it will be available through Sprint and others. But anyway, that's an example of solving a particular problem that's kind of tough, but if you do it, there's a great thing. Some of the problems actually being solved, not necessarily in a systematic way, but just it happened that way. And I'll give you an example. I have one of the researchers who loves to hike in the morning. Okay? And he's normally the first one. So in the hiking trail, there are normally spider webs. So he has to create the spider webs. So he hates spiders. Anyway, used to, until one of his colleagues said, hey, look, spiders are beautiful. Look at the web. It's perfectly balanced and it functions well. And him being a naturally curious person, decided, ask the question, how does spider build a web? Spider is kind of small with respect to the size of the web. It's not particularly smart, and it's nearly blind, can't really smell. So it is like if you're a human being trying to build a web, it's trying to build a 6-story tall web, blindfolded, and oh, by the way, you cannot count the step. That's the task. Okay? And by the way, it's in line. You are not standing from far behind to see whether it's perfectly balanced. So he took an interest in just studying spiders. And he studies spiders. And after a while, he actually realized spiders are something clever. It's really good at checking the tension. So you go out and layer web, and then you check the tension, and you go to a place where tension is kind of not quite balanced, you constantly reinforce it. That's how they build a web. So if you imagine a trampoline, when you, I guess, kids play with it, if you're sitting in the center of the trampoline, you can close your eyes. And because simple tension, somebody jump on it, you know something about what's going on, right? Because there is something going on and you can feel the tension. Well, from this is the genius part. From this, he realized maybe he can apply the same principle in network, complex network. In the network, one of the most challenging problems from the mathematics point of view is optimization. More the complex the network, optimization gets harder and harder, right? For the obvious reasons. What he did was he figured out how to optimize network real time, not static. You know, way they optimize network today is they go by drive-by test because they try to optimize based on the traffic on the road. I mean, I'm talking about wireless network and so on. And then they, increase the power. They play with a couple of parameters, but that's how they optimize it, by brute force. I mean, you have some algorithms and tools to help you, but it's always static at best, and that's the state of the technology. He figured out how to actually optimize the network and realizing that the network doesn't have to know everything. It has to just know what's happening in each neighbor and just share the right amount of information. So we have a very responsive network that to the real-time optimization. What's really exciting about this is that it changes the possibility of not just optimizing, but creating an autonomous network of the future, because the principles are the same. I can talk about a couple of other areas. You know, transformative is that the things that you do that creates the future. Like we went from smaller and smaller devices. So the MEMS device is something that we spend a lot of time just trying to get the size, power, cost down. But eventually we get into the nano area, and we realize actually physics kind of works a little differently here. Applications are quite much wider than communications. So all the sensor work we are doing and so on is based on the continuing effort. We've been working on the MEMS that we need a nanospace. And so this kind of technology, I can talk about a few of those examples, but it's really transformative in the sense. And then here is what I call fountain of youth. I talk about the quantum computers. I don't know whether we actually going to be able to build a successful quantum computers. You know, when I asked my engineers, they said 10 years, $100 million. That was 2 years ago. And I can give them 10 years and $100 million, but I don't think they will do it. I think they're underestimating. So I consider that but if we actually build one, it'd be unbelievable, right? It's just like building a room temperature superconductor, conductor. Yes. So what is this innovation cube has anything to do with how do I conduct my, besides the talk that I give in China. But it actually helped me thinking through how I should manage research. And the whole idea is that you can do research in any of these cubes, but when you are somewhat constrained because of financial resources or timing or whatever, then you have to prioritize. So what I'm trying to show you here is that the Bell Labs are trying to focus more on disruptive type of innovations rather than incremental. That we leave that to the business unit. And then try to also help out the company by, spending more on terms of how do we leverage research into the market. So not really all focus on the future, but also focus on the current market, okay, and let the future market take care of itself. So when you talk about managing this valuable innovation resources, well, at some point, it has to make a difference for the company, which means that you have to transition technology asset into some sort of product or solutions. And you have to do the development, and development is done by business unit. So there has to be a coupling between research and development. And if there's a large separation between what you study and what you develop, then transfer cost can be quite substantial. I mean, with Bell Labs, as you know, we're talking about how we discovered cosmic ray that led to, Big Bang theory and receiving Nobel Prize and so on. I mean, somebody will ask, what does that have to do with communications? I mean, you can make up some stories, but if you believe that industrial labs today, and by the way, Arno Penjas is a dear friend of mine, so I love him dearly, but my point here is that if you are today's Bell Labs, we have to be mindful of the current business environment and has to make sure that our research has a cross-coupling function with the development. But of course, my question is how large the lab has to be, because obviously it's much smaller than what it used to be. Bell Labs of the past was about 3,000 researchers. These are PhD researchers. Now we are about 1/3 of that. So we are much smaller. But is it too small? Or is it too big for the parent company that we are serving? So it's an interesting question to go through. But what I will tell you is this. If you are serving hyper-competitive market, which is our industry, then you have no choice to do disruptive research. If you do incremental research, you actually going to run into innovator's dilemma and eventually die. Okay? So business model has to design to do this, and which is very, very challenging in a business environment, because your business people will tell you that don't do that because it's going to affect my business. I mean, actually, they do worse than that. When I told them that I'm going to build the laptop Guardian, the eBros, our business colleagues said, we are not in the enterprise business. Why are you wasting valuable resources? So you could be consumed with your immediate need and not really focus on that. Matter of fact, I actually mapped every project that we do into 3 categories: research projects, or tech transfer projects, what I call technology integration, or venture projects like what eBros, somebody has an idea, let's just try to solve it, kind of things. And these are real data. And I try to see whether there's the right kind of balance in that. It gives me a visible tool, and I actually try to encapsulate this in mathematical algorithms. People think I'm crazy, but at least it gives me a visible tool that I can sort of see whether we are having a right kind of budget goals and budget priorities. So we use the word a disruptive technology a lot, and I think the word, I think we attribute the concept comes from Joseph Schumpeter, who really talked about creative destruction. And of course, this subject I'm sure we all face. You have to destroy in order to allow a room for the new ideas to survive, right? And it's not a new concept, but it's a concept that we take it quite seriously and have a debate. So when we say disruptive, by the way, let me just take one side point. I had a lot of a dialogue with our Chinese colleagues when I went to give this speech, and there are parts that I didn't talk about. They talk about disruptive, that said, well, the reason the United States, they asked the question, why is the United States so good at creating something new? We in China, we work very hard, just as smart people. Once the ideas are known, we can actually do it better than anybody else, faster, better, and cheaper. But how did you guys get the idea like IMS, soft switch, base station router? Things that, and one of the things that I point out is that in our laboratory, we value diversity. Bell Labs always been global, over 50% people foreign-born, and we value the diversity. Matter of fact, we let the people who disagree with the majority of the people and let them thrive. Not just, tolerant, but let them try. He's a smart enough guy. Whereas in Chinese culture, they value consensus. So I told them that they have a cultural issue to deal with. And also, when you say revolutionary, like disruptive, it's good in English word in the United States. It's bad in China. So again, culturally, they could be a little bit challenging. But anyway, they're talking about the disruption. What point do you decide what you're doing is a disruptive technology or disruptive innovation versus non-disruptive? Disruptive. Well, disruptive means that you're disrupting something, right? Disrupting the market. How do you disrupt the market? You can disrupt the market by technology or innovations, market position of your company, or market character, or create an entirely new market. Market position might be, some car company doing certain type of a process, technology to improve the performance, and therefore got to the number one, rating or a market positions. A example of a market character will be going from the film-based, a camera to the digital cameras on the phone, and what happened to those industry that that serves that market, and then new market will be like a market like advertising. Nobody thought about the web advertising because that technology didn't exist before. But what effect did it have in the printed advertising industry? Okay? And of course, each area has to deal with the magnitude of its impact. It cannot be improving 1 or 2 or 3%. It has to be something substantial. And then how long you're going to have the exclusivity? Any great ideas you have, the competitors are going to try to catch up. Right? And then I will also argue that there are 3 flavors of type of disruption. One is basically deals with the price performance. Okay, and this is the a chart that I got it from Clay Christensen about the innovator's dilemma. I think you are familiar with this. You have a market-leading product, and you try to serve your customers who are adding more and more features. So you make an improvement over that. And somewhere along the line, somebody comes with a low-cost platform, and then basically that's what really needs to be done, not necessarily at this high end, and then you really cannot compete with this low-cost platform, and then you're dead, which is a dilemma. By the way, who knows the answer to this question? Is Elisha Oris. He's the inventor of something, right? What is it? Wrong answer. Elevator was invented 300 years before Christ. He invented brakes. He invented brake so that the elevators can be safer. Until then, if you really look at all the skyscrapers in all the cities around the world, I mean, we have to give him the credit for being able to do this, because until then, people couldn't move the people or equipment safely. So he invented the brake. So it is a really enabling technology. Okay. And then, I guess I have to mention about transistor. When transistor was invented, it was actually trying to solve one problem. That one problem has to do with building a nationwide network, telephone network, and using a vacuum tube. They couldn't get it done because it takes too much power and dissipates too much heat, and also it was too big in terms of volume. So they had to have a new technology to actually get it done. So when they invented transistor, it did exactly the same function of that of vacuum tube. But because of the cost characteristics, packaging characteristics, allow them to miniaturize into integrated circuits and the microprocessors and the personal computers and basically transform the world. It really allowed to realize the things that didn't exist before. So the other types. So we can actually have a disruptive matrix based on the things, the flavor of a disruption impact scenario and the different type of impact that you are making. Sorry about that. Well, how is it useful? Well, it is actually useful from the business perspective. How do you go to the market with this interruption, these disruptive innovations? And I'll give you some examples about where they fit in. So as you do the research, as you think about developing a research assets that can be leveraged in a disruptive way, we got to think through this so that we can actually work with the business unit, because you need their buy-in to execute this. And we have not done well in the past and done well in some areas, but other places we haven't done. So that's the usefulness of this thing. So that's my talk. The part that I talked about is actually the easy part. Real hard part is actually getting it done. Getting it, get the people motivated, and then. So how do you get it done? Well, people talk about thinking out of the box. Well, I think the term came by some consultant who posed a question. But how do you connect these 9 dots with the 4 lines without lifting your pencil? And the answer is you have to go outside the box to make it happen. Well, it's kind of an interesting thing to say. We all like to do this. The problem is that we have this thing called curse of knowledge. We have a harder and harder time thinking out of box more and more as you are experienced, because the thickness of the box that you create based on your forming your experience prevents you from thinking out of the box. It's really so. How do you actually operate where you have to think out of the box, but actually deal with this curse of knowledge? Well, one way I can suggest it to you is have a critical mass of a cross-disciplined approach in terms of natural collaboration. I force my researchers to intermix, not just having a different department in different places, but have them interact more naturally. And so if you have to interact with the people that is outside your comfort zone, outside your area of expertise, it helps you cure that curse of knowledge and be able to think out of the box. Alternative is to think inside the box and live inside the box. And then, a destiny outcome is surely foreseen. That's it. Thank you. I still get the kind of interesting reaction from people when I say I work for Bell Laboratories, and then I have to say, it belongs to Alcatel-Lucent, a French company, and people cannot get over the fact that so many things happen over the last 20, 30 years in our industry, and it's just the amazing transformation